Okay. Okay, that's good. So research has found that neural networks are extremely vulnerable to adversarial attacks. So let's look at what are adversarial attacks. So if I have a classifier and the adversary can perturb an input by a little bit, and then prediction of a classifier can change drastically. So for this panda example, if I add a small noise to this panda, the result image still appears as a panda to human eyes, but the classifier may say it's a gibbon with a high confidence. So we would like neural networks robust against those kind of adversarial attacks. So basically, we don't want any perturbing inputs can induce different predictions. The challenge is there are exponentially many perturbing inputs, and it's impractical to execute all of them. So one solution is to interpret the perturbing inputs as a single abstract input, which is a high-dimensional interval. So what is abstract interpretation in the context of neural network? So let's look at an example. So in this neural network, I have 4 input nodes and 2 output nodes. And I have the values at each input node, which can be a pixel of an image. And the output is the scores for each prediction class. So in this example, the first class has score 0.8, and the score for the second class is 0.1. So the prediction will be the first class. If I perturb the inputs by just 0.1, then I'll get intervals at each input node. And the interval flow to the end of the neural network, and I will get 2 intervals for the output. And in this example, it's artificial. So the output interval for the first class is from 0.4 to 0.9. And the prediction interval for the second class, the maximum value is 0.2. So in this case, the prediction is still like the first class. So let's look at technical details of abstract computation. So the overall goal is to just over-approximate the actual concrete evaluations. And the neural network is just a composition of fine operations and hidden layer operations. It's quite basic to define the abstract transformers for fine operations. We only need to define it for multiplications and additions. The interesting part is the activation functions. So for commonly used activations, such as ReLU or sigmoid, a good thing about them is they are monotonic. So if we want to define the abstract transformer for them, we only need to evaluate at both ends of the interval. So see this example, I have ReLU, and I want to know the abstract transformers at the interval 3 to 5. And I only need to evaluate at the ends, and it's still 3 to 5. So each atomic operation is very efficient to evaluate now, and the overall neural network is also very efficient to evaluate. So all the exponentially many concrete inputs can be efficiently evaluated right now. The problem of abstract interpretation is that it's sound, but it might not be complete. So by soundness, I mean the result always over-approximate the actual evaluation. By incompleteness, I mean the result might not actually reflect the concrete evaluation. So say this example, I have x minus x with input domain 0 to 1. The result from the abstract interpretation will be minus 1 to 1. But x minus x is always evaluated to 0. So the output can be super imprecise, and all the robust inputs might not be certified. So this raises to the research question. Can we have a neural network whose robustness can always be certified using abstract interpretation? And the second question is, if yes, how hard to build this kind of neural network? This leads to our main result, which we call interval universal approximation. So the first part of the result is a yes answer to the first research question. So we can always build a neural network, use any practical activation functions, and the interval semantics on neural network is close to the target function's set semantics. I will explain this in detail later. And the second part of the result is a kind of negative result to the second research question. It is computationally hard to achieve interval approximation. So this demonstrates the power and limit of interval domain for neural networks. So before going to interval universal approximation, let's look at the classical universal approximation. It's classical result that neural networks can approximate any continuous function. So I'm given a continuous function, and my goal is to build a neural network that approximates this function. So by approximation, I mean that for any valid input, the difference between the function and the neural network is very small. So for this example, I have a blue curve, which is a continuous function, and I build a new network, which effectively just a step function, and the difference is very small. Now let's look at the interval universal approximation. So Baader et al. Showed that ReLU networks can approximate any continuous function abstractly. So by abstractly, it means that the input and output are intervals right now. So I have like for any interval, the difference between the output, the difference between the outputs of the function and the new network is small. But wait a second. So the output of this function is like our intervals right now. So what does it mean like their difference small? So this is the interval approximation. So the upper interval is the range of the function over this input, and the lower part is the abstract interpretation of neural network over this abstract input. So I'll have two intervals, and the upper bounds and lower bounds are close to each other. So that's what I mean by interval approximation. And what we did is to extend the result to neural networks with any practical activation units. So this demonstrates the power of interval domain. So with any practical activation functions, one can always construct a neural network whose abstract semantics is arbitrarily close to a target function set semantics. And we call those functions as squashable functions. So it basically just have a left and right limits, and it's monotonic. So for example, a sigmoid function and the soft sine functions. We also show the limit of interval domain. Our construction for this new network uses exponentially many neurons. So a natural question is, can you build such an approximation network efficiently? And we consider range approximation, the range approximation problem. So instead of look at the range of each possible intervals in the input space, I only look at the whole space. So this is simpler than the interval approximation. But even so, we still show that this problem is both NP and coNP hard. So the implications of our results say that it's good that there always exists a certifiable robust neural network, and its robustness can be certified using abstract interpretation. And we can use any commonly used activation functions. But the sad part is that constructing such a neural network is a hard problem. There's no efficient algorithm to compute such a network, which is also polytime executable. So let's look some technical details of this result. So for squashable function, we first show that ReLU-like functions are also squashable. If we look at the gadget, and use that function, we can encode the indicator function. So if we have like step x minus y, I'll have an indicator function for the interval from 0 to 1. And if we dilate this sigmoid function enough, I'll get approximately step function. And similarly, if I use this dilated squashable function, I can build an approximating indicator function for the interval 0 to 1. And indeed, the indicator function for intervals is a quite fundamental object in mathematics. So this means you can use this result to prove our theorem later. So the third takeaway is that the squashable functions can approximately encode a Boolean formula. For example, if I have a Boolean value, the variables x and y, and I have a Boolean formula x and y, then I can use step x plus y minus 1.5 to encode this x and y formula. And similarly, I can use the squashable function to approximately encode this Boolean formula. So now let's look at the proof of RA. So this is quite technical proof. I'll skip most of part of it. But we use the framework adapted from Baader et al. And the critical step is to build an indicator function for high dimensional intervals. So we'll need to first build an indicator function for each dimension of those high dimension intervals, and then we need to put them cleverly. So in this plot, we actually showed a two-dimensional indicator function for the interval 0 to 1 times 0 to 1. And we built it from sigmoid function. So if you look at it, it's actually expected. And now let's look at the NP and coNP in this result. The canonical NP problem is a set problem. So given a Boolean formula, I want to know whether it's satisfiable. And the canonical coNP problem is a tautology problem. So given a Boolean formula, whether all the assignments are true assignments. And indeed, many of the verification tasks are in this nature. I want to know whether all inputs satisfy certain property. And we'll show that the range approximation problem is both NPR and coNPR. So let's first formulate this range approximation problem. So I have a function whose domain is 0 to 1 to the m, and the codomain is 0 to 1. And it's a neural network. Delta range approximating f means I want to find the a and b such that a is close to the minimal value of f, and the b is close to the upper bound of f. So if we look at this closely, if I let delta equal 0, that means I want to find exactly the minimal values and the maximal values of f. This becomes an optimization problem, and because I have no idea what f is, I basically have no assumption except it's a neural network. So this is conceptually a very hard problem. However, if I let delta equals a half, this becomes a trivial problem because I know that the codomain of f is 0 to 1. So I can let a and b be a half, and then then I solve this a delta range approximation problem. So the motivation for proof that RA is both coNP and NPR is the observation that deciding the range of Boolean formula is actually both NP and coNP. So for example, if I know the range of Boolean formula, it can be either only 0, only 1, or both 0 and 1. If I know the result, I will know whether it's satisfiable or a tautology immediately. So for the NP-harness proof of RA, we first need to formulate it as a decision problem. So I define two sets of functions. The first set of functions are those functions whose maximum value is greater than a half plus delta. And the second set are the functions whose maximum values are less than equal to a half minus delta. If I know that I have a function that is from the union of those two sets, I want to decide the exact membership of this function. So if you are familiar with complexity theory, this resembles a gap-producing reduction in complexity theory. When you try to prove some optimization problem, it's hard to approximate. And we'll build a reduction from three sets. The key idea is to simulate the three-thing Boolean formula using Squashable functions. And if I can decide the membership of this neural network, then I can tell whether this three-thing Boolean formula is satisfiable or not. And the coNP-harness proof is similar to the NP-harness one. So it's basically the dual of this part. I mean, that's why it's also called a coNP. It's complement. So let's also look at some other usages of Squashable functions. So a theoretical takeaway is that the property of neural networks is very likely similar to its former counterpart. So for example, in this ReLUs paper, Katz et al. Proved that it's hard to falsify a neural network. By falsify, we mean that we want to find an input that satisfies certain linear constraints on the neural network. And if we view this result from the perspective of Squashable functions, it's kind of immediate. And one practical usage of Squashable function is that it can provide a better verifiable robustness. So this ReLU theta function is essentially ReLU, but we clip it at a point theta. Wang et al. Found that training with ReLU theta function actually achieves better robustness guarantees. If we look at our Squashable gadget for this ReLU function, it's basically ReLU 1. But instead of ReLU1, we have like a ReLU theta, and it's trainable. So those are the works mentioned in this talk, and I want to mark the end of talk with this brainwash meme. Thank you.
Thanks. A reminder again for people online, please post questions in the Q&A tab. Do we have any questions from the audience here? Okay, let me.
Thanks for your talk. It's an interesting paper. I have a question on the interval universal approximation theory. In your theory, it seems that this approximation method they applies to arbitrary activation functions like any activation functions. But then you defined the squashable function where this approximation can works on. But if it works on arbitrary activation function, why you still need to define the squashable function that it can work on? It seems not so clear.
Okay, so we only proved the interval universal approximation theorem for squashable functions. When I say arbitrary, I said arbitrarily practical activation functions. So squashable functions are those practically used activation functions. So it's not arbitrary because from the classical universal approximation result, polynomial activation functions will not provide this kind of universal approximation. So this will not work for polynomial activation functions. Yes. No problem.
Okay, and second question.
It's I think already asked part of it. So like this deep learning community, they come up with, I mean, I would say sometimes every month a new activation function, right? So my question is that you use this term a lot, like you can handle common activation functions. Now there are some properties of these activation functions that makes the optimization problem easier when you're training the network. Something like local dipshit, local dipshit. So is squashable function capturing this class of functions, or is it a uncomparable class?
Okay. So I'm not sure if I get your question very correctly. So one of the recent finding is that if using a ReLU theta function is actually can actually provide a better robustness. The approach is actually like to have a better local Lipschitzness. That's kind of understandable because if I only have ReLU, like it extends till the end. But if I have ReLU theta, it clips at a certain point, then like if I try to verify this process, it's actually easier for the part that's been clipped. So for squashable function, it's kind of similar. Like if I have like ReLU 1 or ReLU something, it's also clipped at a certain point. Then the local Lipschitz is also small or zero or even zero at this point.
My question was more like, what is the relationship between the class of squashable functions and maybe local Lipschitz functions?
Oh,
one includes the other, or?
I mean, they are all local Lipschitz, right?
Okay.
I mean, the global Lipschitz for those squashable functions are basically. I mean, they have limits at both ends. So like they're approaching zero at both ends, and inside there are some nice functions. So they have derivatives, and it's bounded. So they are local Lipschitz.
Okay.
Thanks. That looks like all the questions we have. So let's thank our speaker.